box. And our speaker is Soheil Behnezhad. And he's going to be speaking on nearly optimal massively parallel graph connectivity.
Thank you. Does the mic work?
Your mic doesn't work?
Does it work or no?
All right. Then. Wait, this one does work or doesn't work? Does that one
just
work?
for recording, isn't it?
Oh, you know what? This one works if you don't mind holding it.
Sure.
But you're saying this one doesn't? All right.
Let me see if I can detach it. Yeah, I'm gonna need my hands, so.
Oh, okay. So then we have to figure out how the other one works.
This?
Oh, okay. Hold on.
There's a switch on it? Oh,
Oh, okay. So
thanks.
this one is on.
Okay, thank you. Should I start? Okay. Here I'm going to talk about near optimal massively parallel graph connectivity. This is based on a joint work with Laxman, Dhulipala, Hossein, Esfandiari, Kubalaki, and Vahab Mirrokni. So let me start with the model. So the model is the massively parallel computations model, which is based on MapReduce model of computation and its other variants, such as Hadoop, Spark, and these sort of big data frameworks. So we will be talking about only graphs. So suppose that the input is a graph G with n vertices, m edges, and diameter d, where diameter is the longest, shortest path in the graph. And we assume that the whole model is defined for the cases when the input is too large that it does not fit a single machine. So we have m machines, each with a space S. And this space S is much larger than m, the number of edges, so that we can't put the whole graph in one machine and solve the problem. Therefore, each machine gets a subset of edges. And also, we assume that S times m, which is the space per machine and times the number of machines, which is the total space available in the system, is O of m, so that we don't waste too much total space, right? And so computation in this model proceeds in synchronous rounds. By the end of each round, each machine can compute any function of its local memory, what's stored there. And then at the end of each round, each machine can message other machines. So any pair of machines can communicate. The only restriction is that the total message sent and received from each machine should be bounded by its memory. Right? So you can't receive more message than you can store in your memory. And computation proceeds in rounds until we find the solution of the problem. Right? And what do we want to optimize? We want to optimize the trade-off between the number of rounds and the space available per machine. Right? Okay. So our focus in this talk will be on the graph connectivity problem, and we will specifically focus on the regime of MPC when the space per machine is truly sublinear in the number of vertices n. Right? So the space per machine is n to delta for some constant delta smaller than 1. Okay, so let me start with a simple algorithm which will be very useful. So by the end of this slide, I'm going to convince you that simple local procedures, simple local operations can be done in constant numbers of this model. So basically, suppose that we assign each node of the graph to a different machine, and we store all the incident edges of every vertex on its machine. So there's a technicality here, because the degree of a vertex may be much larger than n to delta, so we may not be able to do this. But suppose that this is the case now. Suppose that the degrees are smaller than n to delta. We assign each node to a different machine. And now, for example, suppose that for this blue node, we would like to compute the sum of degrees of its neighbors. So in each machine, we just simply compute the degree of every vertex, because we have the incident edges. We just count them. And then this blue vertex messages the other machines responsible for its neighbors and asks for these numbers. So within 2 rounds, we can get all these numbers and compute this function. And quickly, for larger degree nodes, we can construct this virtual tree that branches by a factor of n to delta. The depth of this tree is only going to be at most 1 over delta, which is constant if delta is constant. And now this virtual tree construction ensures that the degrees are small and they fit the machines, right? So having this all simple local operations that we'll be talking about in this talk will be implemented in constant number of rounds. Okay. So having this, let me give a very simple log n round algorithm for graph connectivity in this low memory MPC model. So each node marks itself as a leader independently with probability 1/2. And each vertex that is not a leader and sees any leader among its neighbors contracts itself to that leader. So what happens is that, ignoring the singleton vertices, every other vertex has a probability at least 1/4 of being not a leader and having a leader in its neighborhood and getting contracted. So basically, the expected number of remaining nodes drops by a constant factor in every round. And this means that after log n rounds, both in expectation and with high probability, we will have no other vertices left in the graph. And each connected component will be represented by one single node. Okay, so this takes log n rounds. And unfortunately, this barrier says that basically log n round is optimal of a widely believed conjecture. So basically, if you're promised that the input is either a cycle on n vertices or 2 cycles on n over 2 vertices, it's a widely believed conjecture that you require log n rounds to determine which one of them is the case. So if the space is sublinear in n. So basically, this says that the dependency on n is basically settled. Log n is required up to this conjecture, and log n can be achieved. But the catch is, what if the graph has a lower diameter? Can we get a faster algorithm on it? Okay. So there has been some works on this. And in this paper, we show that, well, if a graph G has diameter d, and this d is larger than log n to epsilon for any small constant epsilon, we can find its connected components in log d rounds, O of log d rounds. And if d is smaller, we can find these connected components in log n rounds. So this is never worse than log n, but for lower diameter graphs, it's faster. And the algorithm is randomized, succeeds with high probability, does not require knowledge of diameter d, and uses O of m total space. And we show a near matching lower bound that log d rounds are necessary. Well, that 1 cycle, 2 cycle conjecture already says that log n rounds are necessary in graphs with diameter omega n. But if, for example, one may ask whether for lower diameter graphs, when, for example, d is root n, can we achieve constant round algorithms or not? We show that even if d is polylogarithmic, you will need log d rounds. So this is also optimal. And our algorithm improves over a previous algorithm of Andoni et al., Fox 18, and an algorithm of Asadi et al., Pod C19. So let me actually describe another algorithm, which this time works in log diameter rounds, but uses too much total memory. So in each round, the idea is that each vertex connects itself to all those vertices in its 2-hop. So if 2 vertices are at distance exactly 2, we add an edge between them. So what this does is that after each iteration, you basically shrink the diameter of the graph by a constant factor. So after log d rounds, essentially what you will get for each connected component is a complete graph, which is trivial to solve connectivity for. Right? So after log d rounds, this solves a connected component problem. And the catch is that each connected component becomes a clique. So you will need to store n squared edges at least. And for technical reasons, you will actually need n cube total space. But regardless of that, we need O of m total space. Right? So what if the graph is sparse? Say O of n edges are in the graph. Can we achieve log d round algorithm with O of n total space or not? And this is precisely the question that we try to answer. Okay, so let me informally describe our algorithm. So in our algorithm, we assign to each vertex in the graph a level LV, which is going to be an integer from 1 to up to O of log n. And also for each vertex, we define a budget. The budget is basically a function of this level of the graph. The budget of a vertex is 2 to 2 to its level. And roughly speaking, these budgets control how many edges of this graph we charge to that vertex. Right? So we maintain that the sum of the budgets throughout the algorithm will never exceed m. And having levels on budgets, the algorithm repeats these 3 steps until every remaining connected component becomes a clique. So what are these 3 steps? The first step is that we connect each node up to the amount that its budget allows to the vertices in its 2-hop. So basically, each vertex sees how much budget it has available and connects itself to all those neighbors in its 2-hop. And a technical point here is that you only look for vertices that have a level that's at least your level, so you don't care about vertices of lower level. And you only connect yourself up to the number of neighbors that your budget allows. So this is the first subroutine. The second subroutine is that each vertex that sees a higher level node, so for example, this blue node is of level 4, say, and it has a neighbor of higher level. It picks the highest level neighbor. Here, there's one neighbor of level 8, so it joins this neighbor. So what this means is that you contract this vertex to that vertex. So all the edges are relatable to that neighbor. And if there are many such neighbors, you break ties arbitrarily. And the third, and up to this point, note that we have not yet seen how the levels increase. This happens in the third subroutine. So in the third subroutine, we mark each vertex V as saturated if it has its budget number of vertices connected to it that all have a level exactly equal to the level of this vertex V. Right? We call this vertex saturated if this holds, and also call all of its neighbors of this type saturated. Right? So when this happens, each vertex V that's saturated sees B sub V vertices of exactly the same level in its 2-hop. Right? Now we pick each saturated vertex to be a leader independently with probability roughly 1 over BV. Right? So the idea is that if you have these many neighbors in your 2-hop, you don't want to pick too many leaders. Just picking one leader with probability 1 over BV is enough to be able to see one leader in your 2-hop with high probability. And to be able to say it holds with high probability, we need this extra log n factor. So we pick more precisely each vertex to be a leader independently with probability log n over BV. And each vertex that's not a leader but sees a leader in its 2-hop is contracted to that node. Right? So what happens by doing this is that if a vertex is picked as a leader, roughly speaking, its current budget is BV, but up to BV vertices will be contracted to this node. This is not quite right, but with some work, you can get some guarantee like this. And you can thus, after doing this, increase the budget of this vertex from BV to BV times BV. So there are BV neighbors. Each one of them has budget BV. They're all contracted to this node. So the node that remains can increase its budget to BV to the power of 2. And this allows us to increase the level of the remaining vertex by 1. Right? So this is the algorithm. There are some technicalities that I'm hiding here. So for example, when you're trying to merge to a higher level node, you could end up with chains. We don't want to find the whole chain and then contract all of them. So we just, instead of contracting, we relabel edges and move over the chain. But ignoring this, these details are easy to figure out. And I'm also not going to describe why the total space is bounded by O of M. What I'm going to describe here is why the total number of rounds required by the algorithm is bounded by O of log D plus log log n. Okay. So with this algorithm, the invariant that holds is that after a constant number of iterations of repeating these three subroutines, we can prove that for fix any two vertices at distance exactly 2 at any point in the algorithm. We can prove that after a constant number of repeating these three procedures, either their corresponding distance would be less than or equal to 1. So basically, either they connect, either we connect them by an edge, or they get contracted to the same node, or things like that. Their corresponding distance would be less than or equal to 1. Or if this does not happen, the level of both of them increases by at least 1. Right? Okay. And basically, what this means is that fix any vertex v. After a constant number of repeating these three subroutines, either this vertex v is now directly connected to all vertices that were in its 2-hop, or if this does not happen, then the level of this vertex goes up by at least 1. Right? So in a sense, this means that each vertex resists connecting itself to those in its 2-hop for at most log log n rounds, because the levels cannot exceed log log n. Right? Okay. So what this implies is that suppose, for example, that all the vertices increase their levels within the first log log n rounds. After that, the only thing that happens in the on the graph is that the vertices are connected to those in their 2-hops. And then after log d rounds, you will find the connected components. But the argument is not as easy as this, unfortunately, because it's not the case necessarily that all the vertices increase their levels initially and then they connect to hop. So we need a more specific argument for this. But it's also almost simple. So the argument goes as follows. So pick any two vertices in the graph initially and take any arbitrary shortest path between them. There will be at most d nodes in this shortest path, because that's the diameter of the graph. And we put one token on each vertex of this shortest path. So there will be at most d tokens. So after each round, some vertices, the green nodes here, increase their levels, and those that don't increase their levels are connected to those in their 2-hop. So what we do is that now we drop those vertices that are, so for example, there is a let me use the, never mind. So so for example, there is a link between these two nodes, so we can drop this node from this shortest path. So once we do this, we can now pass all the tokens of this vertex to this white node that connected to hop. Right? And we repeat this. Right? So again, some vertices increase their levels, and some don't, but connect to their 2-hops. We drop nodes for those and pass their tokens to those neighbors. So what happens as this process goes is that if a vertex remains to be of low level, then it collects a lot of tokens. And so what we prove is that if you resist being connected to the vertices in your, if you don't increase your level for, say, k rounds, then the number of tokens that you have is at least some constant to the power of k. Right? And having the fact that there are at most d tokens in the whole path initially, this cannot continue for more than log d number of rounds. Right? Okay, so in conclusion, we showed that graph connectivity can be solved in log d plus log log n rounds. And note that this log d term is usually dominant unless the graph has a very low diameter. And we also show that log d rounds are really necessary under the 1-cycle, 2-cycle conjecture. So the questions that remain open is, well, first of all, can we get a clean log D round algorithm or not? So our algorithm is log D so long as D is larger than log n to some constant larger than 0. But so for example, suppose that D is log star n. Can you design a log of log star n round algorithm or not? And another open question is, what other global problems admit such log D round algorithms? Thanks. Yeah, so if D is constant, so O of D round algorithms are trivial. Yeah, if D is constant, you know how to do it.
Any other questions? Oh, yeah?
So, I think you mentioned about that in the theorem algorithm, you need some primitive to prefix on the concept give about the
Uh-huh.
So basically, maybe it's possible to design a logic round algorithm for theorem and arbitrary theorem.
That's a great question. We don't know the answer. Yeah, that's a very specific type of theorem that we work on.